Swayam Prabha. Digital India. Educated India.
So today we shall discuss the transshipment problems, concepts and examples. And first of all, let's take a very quick review of what we have already discussed about transportation problems in a brief way. Let us quickly see some of the things. So what had happened in a transportation problem? Materials are transported at a minimum possible cost from a set of sources with availabilities to a set of destinations with demands. And unit cost of transportation is known. So these we already known. And apart from that, we had also discussed that transportation problems are solved, first of all, for additional constraint, that is sigma AI equal to sigma dj. That means the total availability should be equal to the total demand, and that reduces one basic variable because we are adding one additional constraint, and this is the formulation: minimize z equal to sum over I sum over j Cij xj subject to sum over xij over j equal to aij and sum over xij over I equal to dj. Right. So how many basic variables? M plus n minus 1. Why I repeated this? Because in transshipment problem, these results are all going to be true. Because initially, after taking the transshipment consideration, we shall transform the transshipment problem to a transportation problem, and thereafter solve the transshipment problem with the transportation problem algorithm. So let us first proceed and see what are the things. So these are some basic assumptions we have already discussed. Production cost is same everywhere. Transportation cost need not vary as distance. This is the third point, which is the most important. There is no transshipment. So this is the basic assumption of transportation problems. That means there are no intermediate nodes and no movement from source to source, destination to destination, or destination to source. Only source to destination is allowed. So this is a basic assumption of the transportation problem. Apart from that, there are no restrictions to any supply from a source to a destination. Anyhow, now these particular constraint we are going to relax. That means not only the source to destination, as I have just now shown in the previous figure, but also, there could be source to source, destination to destination, or even destination to source movement. And there could as well be some intermediate nodes. So now let us proceed with the definition of a transshipment problem. So a transshipment problem is a transportation problem with some additional consideration. What are they? There could be intermediate nodes. There could be transportation of material from source to source or destination to destination or destination to source. These are in addition to the source to destination consideration. So can you tell me how exactly we can construct a transshipment matrix once the transportation matrix is available? Can you think of that? How do I also take not only source to destination, but also source to source, destination to destination, or even destination to source kind of transportation? How is it possible? How do I do? How do I suppose there are two sources and three destinations? So what exactly should be done? Right. So now you are correctly saying that. So suppose you see we had 2 into 3 matrix. So the two sources, and there are two sources and three destination. Now if a destination can also be a source and source can also be a destination, and you can even have source to source and destination to destination. So what you can do, you can transform these to a 5 by 5 matrix. Instead of 2 by 2, you can now think of there are 5 sources as well as there are 5 destination. So what happens? The destination is also a source and the source is also a destination. But while doing it, you must remember that although the source is also becoming a destination, source as a source and source as a destination, their behavior patterns are different. They are not same. So that fine distinction should be remembered, because you see, when it is a source, it has an availability. But when it is a destination, it may not have any demand. So in that sense, it is only used as a destination in the sense that it is used as a transshipment node. That means materials are being passed through this node. As such, the source doesn't have any demand. If it has a demand as well as a source in the beginning, then it cannot be called a source. Then in that case, it should be called a transshipment node in the beginning. Anyway, all these discussions will continue with an example. Now look here, this is a problem. In this particular problem, what happens? There are 3 factories and there are 3 warehouses, and it's a typical transportation problem to begin with. With demands 200, 300 and 400 and availabilities 300, 400 and 200, so that it is a balanced problem and total availability and total demand, they are equal. And these are the cost figures 232, 113 and 321. They are all given. So if we are asked to solve this problem as a transshipment problem, so solve the transshipment problem and compare the solution with the transportation solution. This is the problem we are taking up. So transshipment unit cost from F1 to F2 is negligible. That is 0. So transshipment unit cost for all other cells are 1. So what it means that not only from factory to warehouse, but you can also send material from factory to factory, warehouse to warehouse, or even warehouse to factory. Now all these transshipment costs are taken to be 1. Is it not? Only one cost is 0, that is F1 to F2. So if you send some material from F1 to F2, then that cost is 0. So as some of you have very rightly said that you have to take now all factories are also to be considered as warehouses and all warehouses are also to be considered as factory. If that is done, then what should be the size of the matrix? So it should be 6 by 6. But having said that, and I have also written in my previous slide that 2 into 3 becomes 5 into 5. But that is not a general rule. We have to see one more thing. That one more thing is that is there a factory, that means a source, which is a pure source, or if there is any destination, that is a pure destination. So if there are some pure sources and there are some pure destinations, we can leave them alone. See, if there is a source through which no material can pass, that means it cannot be a thought of a destination. Is it not? That means, no other factory or warehouse can send material to this particular factory. Then we can leave it alone as a source and we need not take it as a destination. Please understand this. So that is what we are going to discuss. But before that, let us first solve the transportation problem and keep that transportation problem as a basis for comparing with our results that we are going to get for the transshipment problem. So this is a simple solution. So here are the Vogel coefficients. So since it's a minimization problem, 2 is minimum. So 0, 1, 1, 0, 1, 2, 1, 1, 2, 1, 1, 2, 1, and 1, 2, 1. So these are the initial values 0, 0, 1 and 1, 1, 1 as the minimum penalties. We have to begin somewhere. So we begin at, because there is a tie. So we begin with one of the 1 and we see that we make an entry of 200, right? So after making this 200, this 1 goes out. And then this one, because now it is 110, now 1 gone. So now the minimum cost would be 3 minus 1 equal to 2. So then we make the second 200 entry, and this row is gone. So this column was filled up, then this row is filled up. We put a 200 there, and after that again we revise the penalties. So this is gone, and since these two things are gone, then this also revised to 1. And then after that again we have tie 111. So we choose one of them. So we choose maybe this one, and we make an entry of 100. And once we make, then two rows and some two columns and one row is taken care of. So that means we have no other choice but to fill up the 300 and 100. So this is the VAM solution, that is the Vogel's approximation method, gives a good initial solution. After that, we compute the UV coefficients. We start with say 0 here, then we get some 1, we get some 1, and because of this 1 we get this 1, because of this 1 we get this 0, because of this 0 we get this 2. And thereafter we compute the Cij minus Zij values, and we see that there is a -1 and there is a 0. So because of -1 we make some entry, and closure is obtained, increase F1W1, decrease F2W1, increase F2W2, decrease F3W2, increase F3W3, and decrease F1W3. So closure is obtained. So who will tell what is the minimum amount that can be transferred to F1W1? I mean maximum
100.
amount. Maximum
100.
amount that can be transferred to F1W1 is 100, because 100 is the maximum that is going down. So then accordingly we make changes, and this is our solution. So 100, 100, 300, 200, and 200. Again UV coefficients are computed, and then we find all of them are positive. So this is the optimum solution, right? So transportation optimum solution is obtained, and the optimal transportation solution is now obtained. All the UV coefficients are computed again along with Cij minus Zij values, and all the Cij minus Zij values are now positive. So total cost at this point is 1200, right? 100 into 2 plus 200 into 2 plus 100 into 1 plus 300 into 1 plus 200 into 1, which means 600 into 1, that is 600, and 300 into 2, that is another 600. So 1200. So that is the transportation solution. All right. Now, if we have to now solve the transshipment problem, we had to take certain consideration. So what are those considerations? But before that, graphically, this is how the solution could be represented, right? So what is happening? This particular solution, if you really look, F1W1 is 100, F1W3 is 200. So F1W1 is 100, F1W3 is 200. Then F2W1 is 100, F2W2 is 300. So F2W1 is 100, F2W2 is 300. And finally, F3W3 is 200. So F3W3 is 200. All right, so this is graphically the transportation solution which is shown here. Is it all right? So you can see that balance is all happening here. The availability is 300, 100 plus 200 is 300, 400 at F2. So 100 plus 300 is 400. F3 availability is 200, that 200 goes to W3. And at demand points, W1 total receives 100 plus 100, 200. So demand is met. W2 300 and demand is 300, it is met. W3 200 plus 200, 400, demand is met. So this is the solution. We shall again get back to this diagram after we solve the problem as a transshipment problem, right? So let us now see some of the important consideration for the transshipment. So first of all, since transshipment allows source to source, destination to destination, as well as destination to source movement, we have to identify the following. So number of sources. So you see, initially it is easy to say that it should be the sources plus the destinations, but no, we can reduce the matrix size because 5 by 5, in this particular case it's a 3 by 3 matrix. So if you take all sources as destinations and all destinations as sources, then you have to work with a 6 by 6 matrix. But if we can reduce the size, then it is always better. So what we can think that if there are some pure sources which actually does not work as a destination, then we can reduce such numbers. So you must understand that total number of sources are equal to pure sources plus transshipment nodes, and number of destinations would be pure destinations plus transshipment nodes. All the sources will have availabilities and all the destinations will have demands. The details are to be worked out. So we have to work out the details. But before that, we must understand what is a pure source, what is a transshipment node, and what is a pure destination. So here are the definitions. Pure source, sources that do not allow any transshipment. This means they are not to be used as destinations. Pure destinations, destinations that do not allow any transshipment. This means they are not to be used as sources. Transshipment nodes, these are used both as sources and destinations. This means they allow transshipment. Now go back to this diagram in the original problem. So here is the original problem. Now tell me, is there any pure source? There are three sources, F1 to F2 to F and F3. Are all of them pure sources, or one of them pure sources, or two of them pure sources, or none of them are pure sources? There are no pure sources. So thank you. It is definitely so, because you see, if you read this problem carefully, then transshipment unit cost for all other cells are 1. That means all transshipments are allowed. That means F1 can send to F2, F1 can send to F3, F1 can send to W1, W2, W3 as usual, but also W1 can send to F1, W2 can send to F1, even W3 can send to F1. So because all transshipments are allowed, F1 is not a pure source. So if F1 would have sent to only W1, W2, W3, F2 and F3, but if it is not used as a destination, that means W1, W2, W3 cannot send to F1, then we would have said that F1 is a pure source. Is it all right? So that is the essential idea of a pure source. Now tell me, W1, W2, W3, are there any pure destinations? So that also yes, because there are no pure destinations in this particular problem. There are no pure source and there are no pure destinations. Is it all right? So destinations that do not allow any transshipment, that means that, transshipment in the sense destination are destinations. So if there is one destination sending to another destination, then the destination is being used as a source. Is it all right? So, however, if a destination receives material from, suppose there are 3 destinations, 2 destinations can send material to one destination. So that is fine. But other 2 destinations that are sending material to the 3rd destination, they are not pure destinations because they are also used as sources. So in this sense, you have to define pure sources and pure destinations. Thereafter, the rest of them, which are used both as sources and destinations, which allow transshipment through those nodes, they are called transshipment nodes. Then we have to define another very, very important concept, which is known as the buffer amount. So buffer amount is the maximum amount that can be used towards transshipment through the transshipment nodes. So, buffer amount B is the maximum of total supply and total demand. If total supply is 900 and total demand is 1200, then the buffer amount would be maximum of 900 and 1200, that is 1200. Go to the diagram once again and let us try to understand, what is the buffer amount. Look here, in this particular problem, the total supply or total availability is 900. Total demand is also 900. So what would be the buffer amount? Buffer amount would be maximum of, total availability and total demand. So how much is that? No, it will be 900 because total availability is 900, total demand is also 900. So that means the buffer amount B would be maximum of 300 plus 400, 200 plus 300, plus 400, that is equal to 900. Right. So that is the buffer amount B. Now, once we understand the buffer amount, see what is happening. Supposing the amount is to be supposing, we are doing some transshipment, but we don't know what is the maximum amount that could be transshipped through a particular unit. Now, suppose F1 availability is 300, F2 availability is 400. Suppose F1 sends its entire material to F3, F2 sends its entire material to F3. So at this current time, F3 is now having 900 units, isn't it? So you see, that is what is the buffer amount all about. So maximum amount that F3 may actually handle is equal to the buffer amount, that is 900. I hope I made myself clear that the total supply or the total demand, whichever is maximum, that is the maximum possible amount a particular unit, either a source or destination, is going to handle, and that is the significance of the buffer amount. So is there any question on buffer amount? Are all of you clear about how to define buffer amount and what is the significance of buffer amount? It is the maximum possible amount that a particular source or a destination or a transshipment unit is going to handle. Is it all right? So it is given by the maximum of total supply and total demand and equal to the buffer amount. And it is a very important requirement for solving a transshipment problem. Right? So if there is no question, I'm going forward. Now, redefining the availabilities and demands. So see, availability of pure source equal to original availability. Demand of pure destination equal to original demand, because there is no transshipment through them, right? So no transshipment through them. So therefore the buffer amount is not going to go through the pure source or through the pure destination. They are going to handle only the original availability or the original demand. Now, availability of transshipment node. See, transshipment nodes are used both as sources as well as destinations. So availability of transshipment node equal to original availability plus the buffer amount. And demand of transshipment node equal to original demand plus the buffer amount. I hope I made myself clear. The availability of the pure source or pure destination or demand of pure destination, they are not going to change, but availability of transshipment nodes, that means the sources and destinations which are not pure, or if there are some intermediate nodes, they have to be, they might have availability, they might have demand. See, some transshipment nodes are having availability, but no demand. Some other transshipment nodes are having demand, but no availability. Is it all right? So that we have to be very careful, because they are occurring as source as well as destinations. We have to add 900, that is fine. But they may or may not be having original availability or demand, and we have to understand the problem as the case may be. Is this definition clear to all of you? So pure source and pure destination, we are not going to change any availabilities or demand, but for transshipment nodes, we are going to add the buffer amount with the availability or the demand as the case may be. Right. Now, having said that, this is the steps which are required to obtain the transshipment matrix. first state, define pure sources and pure destinations, the PS and PD. Define transshipment nodes Tn. Define buffer amount B. Obtain a matrix with PS plus Tn sources and PD plus Tn destinations. Obtain availabilities of pure sources and demands for pure destinations. Obtain availabilities of transshipment nodes as sources. Obtain demands of the transshipment nodes as destinations. Then compute the unit costs or unit profits of all the cells. All right, so these are the steps. I will again repeat this slide when we take up the transportation problem to transshipment. So once again, this slide I have already shown. So this is the transportation solution, and already we have found that optimal transportation solution is 1200. Solve now the transshipment problem with the following. Transshipment unit cost from F1 to F2 is negligible, that is 0, and transshipment unit costs for all other cells are 1. All right. So here are some of the things. There are no pure sources and no pure destinations, as you have already said, all because there are transshipment happening between all cells, right? And the cost is 1. And all F1, F2, F3, W1, W2, W3 are transshipment nodes. So it is a 6 by 6 matrix. Buffer amount B is maximum of 900 and 900, that is 900. The matrix will be 6 by 6, PS plus Tn sources by PD by Tn destinations. No need for pure source availabilities or pure destination demands. Transshipment node availabilities as sources are obtained, that is add 900. Transshipment node demands as destinations are obtained, add 900. Unit costs of all the cells are computed. Is it all right? So these are some of the facts which we have already understood, and therefore let's go ahead with the transshipment matrix. Now look here, these are the sources we have now got: F1, F2, F3, W1, W2, W3. And these are the destinations: F1, F2, F3, W1, W2, W3. Look, the original transportation matrix I have now identified as a, this particular square. So if you think of these as 4 different squares, so this is one square. It may not be square all the time. In this case, it is a square. In other cases, it will be a rectangle, because there are 3 factories and 3 warehouses. That's why it's a square. Anyhow, so this is the original transportation problem, right? So this one is factory to factory. This one is warehouse to factory, and this one is warehouse to warehouse. So you see, all kinds of transshipments are taking place here, here, and here. Is it all right? So different transshipments could be represented, and this is the original transportation matrix. So original transportation demands for the 3 warehouses were 200, 300, and 400. And original availabilities for the 3 factories were 300, 400, and 200. All right. Now, since everything is a transshipment node, the buffer amount is added with all of them. Is it clear how the availabilities and demands are found out? Look here, these factory as a source, it has some availabilities. These warehouses as destinations, they have some demands. But these warehouses as sources, they had no availabilities. And these factories as destinations, they had no demands. So for them, only buffer amount. But warehouses, since they have demand, the original demand is added with the buffer amount. Same thing for the row wise also. Any question on this? All right. So I hope you have understood. Now comes the cost. Now, when it comes to the cost, obviously these costs are all known. F1 to W1, F1 to W2, F1 to W3, etc. The transportation matrix costs are all known. Now, it is said that all other transshipment costs are 1. So if you blindly put 1 everywhere, you will be actually wrong. Because look, the long diagonal is very important to note. The long diagonal is F1 to F1, F2 to F2, F3 to F3, W1 to W1, W2 to W2, and W3 to W3. Now tell me, is it possible to send any material from F1 to F1, F2 to F2, F3 to F3? Actually, they are meaningless, is it not? See, this long diagonal is actually, they will serve a very important purpose. As such, they mean nothing. Because if some material is there in F1, sending it to F1 has no meaning. It's all right. So that means all such costs along the long diagonal will be zeros. And these cells are actually, they will be used for a very specific purpose. Later on, it will be clear to you what is that purpose. So, this is the transshipment matrix. So these are the availabilities, these are the demands, these are the original transportation costs. What should be the transshipment costs? All right. So that is the question. Now here you see all transshipment costs are 1. So I have filled up all 1. But note this cell. You see the long diagonal. Please note they are all zeros, because there is no meaning in sending F1 to F1, F2 to F2, etc. And it is also mentioned that F1 to F2 is negligible, so 0. All right. So these F1 to F2 is 0, not because of any general thing, but because it is given that all transshipment costs are 1, excepting F1, F2, which is 0. So that is how this 0 has come. But this long diagonal, but it won't be long diagonal in all problems, because in other kind of problems, where F1, F2, F1 to F1 or F2 to F2 may not be on the long diagonal, because assume a matrix 5 by 6. Obviously there, it won't be the long diagonal anymore. So, anyhow, there will be some cells definitely of this type. They will be all zeros. Right. So this is how the cost matrix is obtained, and these are the demands are obtained, the availabilities are obtained. That means now the problem can be solved as a transportation problem. So transshipment initial solution. Now comes a very interesting observation. Initial solution for the transshipment problem can be obtained by making use of the Vogel's approximation method. If there are no pure sources and no pure destinations, and total availability equal to total supply, that means there are no dummy sources or dummy destinations, then a quick method of getting an initial solution is as follows. Fill up the transportation in the transportation part of the matrix. Fill up the long diagonal with the buffer amount B. There should be required number of basic feasible solutions. So this is a quick method, but this quick method is not applicable everywhere. So as a general rule, you can follow VAM to get a quick initial solution, right? But sometimes, particularly if there are no pure sources and no pure destinations and there is no dummy, then this method can be applied. So we applied this method and see a quick initial solution is obtained. That is, this is our transportation solution, and these 900s are occupying the long diagonal. You see, totally there are 6 sources and there are 6 destinations. So 6 plus 6 minus 1, there should be 11 entries. There are 5 entries in the original transportation matrix, and there are 6 more entries along the long diagonal. So 11 entries are all available. You see, this is how the transportation solution can be shown in the transshipment matrix, right? So this is basically nothing but the transportation solution. That means there are no transshipment. There is no transshipment because the entire amount that is supposed to be transshipped, is going through the long diagonal. That means there is no meaning in sending F1 to F1, F2 to F2, etc. So therefore, if we put full 900 along the long diagonal, which means basically there is no transshipment happening. So in a sense, this long diagonal is being used as a dummy, as some dummies. Using them, the transshipment initial solution can be obtained. And if you look at, all are perfectly balanced. So you see F1 demand is met, F2 demand is met, F3 demand is met, W1 demand is met, 200 plus 900 is 1100, W2 demand is met, 300 plus 900 is 1200, W3 demand is met, F1 availability is met, 900, 100, 200, same with F2, F3 and W1, W2, W3. All right, so the matrix is perfectly balanced. But the question comes, is it optimal? If it is optimal, then there are no transshipment opportunities. That means you can definitely do a transshipment, try having a transshipment, but there are no such opportunities. There is no change in the cost structure because the transportation solution is returned as the transshipment solution. So how to know whether this is an optimal solution or not? Compute the UV coefficients and find out the Cij minus Zij values. So this is precisely which is done here. So this is the iteration 1 with the UV coefficients. So we put one of them as zeros. So this is as 0. So by putting it as 0, we get a 0 here. We get a 1 here. We get a 1 here. Now, because this is 1 and this is 0, so we get a minus 1 here. Now, this 0 and 0 and this 1 we got, and there is a 2. So this should be 1. Because of this one, we get minus 1. Because of this one, we get 1 because it is 2. And because of this one, we get a minus 1. So like this, we can obtain the UV coefficients and thereafter compute the Cij minus Zij values. Now, interestingly, if you observe, these all are ones, but, there is a 0 and that 0 is F1, F2, sorry, there is a 0 at F1, F3 and there is a minus 1 at F1, F2. Is it all right? So therefore, we can understand that there will be some entry here. So let us try to make that entry. Let us try to make that entry. So if we make some entry here, now tell me how the balance is obtained. So obviously this has to go down. Which one should go up? So F2W1 should go up and F1W1 should go down. Right? So this is how you can complete the closure. And if you complete the closure like this, then you see the maximum amount that can come to F1, F2 is 100. Right? So this 900 becomes 800, this 100 becomes 200, and this 100 goes out. So this is how, the same thing what I have done in the previous slide is shown here, that this is going to be a square which is going to be important. So now that has been done, that this 100 has been put here, and this it becomes 800 and this becomes 200. Is it all right? So this is how the next iteration is obtained. Once again, the we have tried to compute the UV coefficients. In fact, there are no changes in the UV coefficients. And when we try to find out the values, we find that this is the optimum solution. Although, there are 4 zeros, as many as 4 zeros are there. All right, that is F1 to F3, F2 to F3, and W1 to W3 and W2 to W3. So we'll not do it, but let us at least see the implication of them. What is the implication? Yes. So if we make some entry here, just look how the closure is obtained. This is right. Sorry. So this goes up and this goes down. So look how the closure is obtained. The closure is obtained by transferring further some material that is F1 to F3, and therefore there is no direct sending of F1 to W3, rather directly sending the material of F1 to F3, and from F3 then you send to W3. All right. So this is the implication of one of the alternate solution. All right, so you see, if you now compute the cost, because they are all zeros, so 200 into 1, 300 into 1, and 200 into 1, so 700, and 200 into 2, so total cost is 1100. So what happens by considering transshipment, you are reducing the total cost by 100. All right. So see, this was the transportation solution. Total cost was 1200. And when we had transshipment, what it says that send the F1 material not to W1 directly, but send it to F2. All right. Send it to F2 and let F2 send the entire demand of W1, that is 200, because F1 to F2 no cost. Probably F1 and F2 are in the same premises, and as such maybe sharing the same kind of setup. So therefore F1 F2, but they are separate, so instead of making F1 some effort to send to W1 and F2 separately making some effort to send to W1, let F1 send its material to F2 and F2 then send it to 200. And we have seen an alternate solution. Even it says that do not send material to F1 to W3, send F1 material to F3 directly. That means, do not send F1 to W3 also. In fact, let F1 send nothing. It only sends F1 to F200 and F1 to F3 200, and then F3 send the entire material to W3, that is 400. Is all right. So like these, various transshipment options are possible, and those transshipment options, not always, but sometimes, if the facilities are appropriate, then are going to reduce the costs. Is it all right? So I hope you have understood how the transshipment is helpful and how certain transshipment options opens up new dimensions of saving costs or increasing profit in transportation problems. Now, having said that, let us take one more problem quickly and try to solve it from the transshipment point of view. So here is the problem that there is two sources and there are two destinations. Here, however, the availability and demand, they are not equal. If you look at the total availability is 100 and 250, that is 350, and the total demand is 400. All right, and there are different transshipment costs. The three different matrices are given, that is S1 to S1 is 0, S1 to S2 is 1, S2 to S1 is 1, S2 to S2 is 0, D1 to D2 is 2, D2 to D1 is also 2, and also D1 to S1, D1 to S2, D2 to S1, and D2 to S2 are also given. In fact, that is the same matrix. It should be transpose of the original matrix, but the costs are same. That means S1 to D1 and D1 to S1, both are costing same. So here the transshipment options are available and all transshipments are possible. And however, there is a difference, that is the total availability and total demand, they are not equal. All right. So solve the transshipment problem. Note that total availability is not equal to total demand, and transportation and transshipment unit costs are indicated. So tell me first of all, how many sources and how many destinations this problem is going to have? Will it be 4 by 4? Why it is 5 by 4? Where is the additional one coming? Correct. So you see, it needs a dummy. You can do in this problem in a different way also. You can solve the transportation problem by making it 3 by 2, isn't it? 3 by 2, and then you can see that SD that is not going to be the dummy source is not going to be because it's a pure source. So you can think in that line, and you can also solve it in that manner. Understand what am I saying? That first make the transportation problem as a balance problem, and make it a 3 by 2, that is S1, S2 and SD, and after that D1 and D2, and so therefore 3 sources and 2 destinations. But since SD is a pure source, that is it's a dummy, and it cannot have material, therefore we can simply say that SD is a pure source, S1, S2, D1, D2 are transshipment nodes, so therefore it's a 5 by 4. So you can think in two ways. One is just think all 4 are pure source transshipment nodes, so 4 by 4, but a dummy is required because there is a additional demand than the availability which can be made from a dummy source. Anyhow, whichever way you think, the matrix size will be 5 by 4. In fact, it is easy to really conceive that first make the transportation problem balanced and take a dummy source, and then you realize that the dummy source is a pure source, so it will be there only on the source side and it will not be on the destination side. Right. So having done that, let us see some of the facts. There are no pure sources or pure destinations the way I have seen it. Buffer amount is B equal to maximum of total availability and total demand. Here the figures are different. So buffer amount is 400. Transshipment node S1, S2, D1, D2. A dummy source SD is added with availability 400 minus 350 equal to 50. And availability and demand of the transshipment nodes are calculated. All right, so this is how the transshipment problem can be formulated in this particular situation. So look here, this is the S1, S2 and D1, D2. This portion is the original transportation. So 100, 250 and 200, 200. Thereafter we add the demands 400, 400, 400, 400. That is the buffer amount, and 400, 400, 400. And SD is like a pure source. So 50 here, and no buffer amount is to be added because nothing can come to SD. It is only for the balancing the remaining amount. So the total is 2000 from both sides, and the cost matrix is replicated. So 2446, 2446, 0. But this matrix is the transpose of this matrix, because these two fours are same. Looks like it is the same matrix. In reality, it is not same matrix. It is the transpose of this matrix. Anyhow, so 0, 1, 1, 0 and 0, 2, 2, 0. All right, and SD has all zeros for the costs. Right, so this is how the transshipment matrix is obtained. Now, how to solve this problem? How to get an initial solution quickly? Which method should we use? Here there is no other choice because we have not solved the transportation matrix. It is not always necessary that we solve the transportation problem separately. It's not required. We can take the transshipment problem itself as a problem and solve it from the beginning. So here the VAM solution is shown. We obtain the minimum penalties, and the minimum penalties are made use of to obtain the VAM initial solution. So if you look at initially, they are all 0, 0, 0, 0 because of 2 zeros everywhere, and this side they are 1, 1, 2, 2. So one of the 2 has to be taken. So this 400 is entered. Like these we follow, and we get the transshipment VAM initial solution. So you have to do these things so that you get practice. Right? Please do some of these problems. So here there are 5 sources, and there are 4 destinations. So there should be 5 plus 4 minus 1, that means 8 entries. So 1, 2, 3, 4, 5, 6, 7, 8 entries are there. That means required number of basic feasible solutions are there. So we found that the VAM initial solution cross check can be made 150 plus 250, 400, 400, 600 and 600, and here also 500, 650, 400, 450. So they are all matching. So after the VAM initial solution, then we compute the UV coefficients. So if we put the 0 here, so it becomes 0, 2 and 4. This 4 would give 2 minus 4 here, and this 0 would give a 1 here, this 1 will give a minus 1 here, and this 2 will give a minus 2 here. Then if you compute the UV coefficients, you see they are all plus, excepting there is a 0 at D1, D2. All right. So this D1, D2, you can make some entry there. Then this should go down, this should go up, and this should go down. So that means 150 can be put at D1 to D2. That means that is going to be the alternate optimal solution. So this is how this particular transshipment optimal solution looks like. What is really happening? We are sending the 250 material that we are having at S2 to S1, right? So look here, the S2 is sending 250 to S1, and see what has happened to the long diagonal. The long diagonal is here. All right, it is not exactly ending at a corner because the presence of SD, but nevertheless there is S1 to S2, S2 to S2, D1 to D1, D2 to D2 that you must identify. So since S2 to S1 is 250, it means that S2 material is completely sent to S1. All right, and then the total amount, that is 350, is available, and that 350 is divided 200 to D1 and 150 to D2, and remaining 50 is coming from the dummy source. 50 goes to D2. So this is the optimal transshipment solution, and TC here, I don't know whether that calculation is correct. TC is 1250. All right, TC here is 1250, not 1100. All right, and here that is the alternate optimal solution. So in this alternate optimal solution, you see that S2 to S1 is there. Additionally, we have a D1 to D2 150, right? D1 to D2 150 is also obtained, and S1 to D1 is 350. And so these are the changes that has happened. And if all these changes are taken care of, then we see this is the alternate solution, which looks very simple also. That dummy sends 50 to D2, S2 to S1, 250 you send to S1. S1 sends the entire material to D1, that is 350. D1 sends, after taking its requirement of 200, 150. So this is not 1100, this should be 1250. So D1, D2 should be 150, and that is how the transshipment alternate optimal solution is obtained. Is it all right? So basically, first of all, what is required in transshipment problem? You have to identify the pure sources, pure destinations, and transshipment nodes. Thereafter, you have to compute the buffer amount. You have to compute the costs, and you have to see whether some dummies are required. And after that, the matrix has to be, completed. If, the transportation solution is available, and we have a pure matrix, then we can use the transportation solution to get a quick initial solution. But that method may not work all the time. It has worked for that problem. Otherwise, you have to use Vogel's method to get a quick initial solution, and then solve the problem, and then interpret the solution. The interpreting the solution in the form of plot is also very important, because that plot actually shows where the transshipment is actually happening and where the cost is actually saved. Is it all right? So that is all for today, and thank you very much for patiently hearing today's lecture.